Welcome back, everyone. Fusion power has long been considered the ultimate energy source because it seeks to replicate the same reactions that power the sun. Italy is deeply involved in this effort through collaborations with European partners and international research projects. In this video, we will look at how Italy contributes to fusion research, what physical principles are at work inside a fusion reactor, which institutions and companies are leading the charge, and what challenges remain before electricity from fusion becomes part of daily life. The central principle behind nuclear fusion is the merging of atomic nuclei to release energy. Most experiments attempt to fuse isotopes of hydrogen, usually deuterium and tritium, because these have the lowest energy requirements for starting the reaction. When these nuclei combine, they form helium and release a neutron along with large amounts of energy. Unlike fission reactors that split heavy atoms such as uranium, fusion avoids long-lived radioactive waste and offers a much higher energy density. The scientific challenge is that fusion requires temperatures of over 100 million degrees Celsius and stable containment of a hot plasma. One of the most widely studied designs for fusion is the tokamak. This is a large donut-shaped magnetic chamber that uses strong magnetic fields to confine the plasma so it does not touch the reactor walls. Italy plays a role here through the ENEA research agency, which supports work on magnetic confinement. ENEA, the Italian National Agency for New Technologies, Energy and Sustainable Economic Development, operates facilities that test superconducting magnets and plasma heating systems. These technologies are vital for the larger ITER project in France, which is currently under construction and represents the biggest tokamak ever attempted. ITER, or International Thermonuclear Experimental Reactor, is a multinational project that includes the European Union, Japan, South Korea, India, Russia, China, and the United States. Italy contributes through components and scientific expertise provided by ENEA and by Italian companies contracted to supply critical parts. For example, Ansaldo Nucleare and ASG Superconductors, both based in Italy, are manufacturing key magnetic coils for ITER. These coils will create the intense magnetic fields necessary to hold the plasma in shape. The ability to build such massive superconducting magnets demonstrates the engineering capacity Italy brings to international collaborations. Another important aspect of fusion research in Italy is the Frascati Tokamak Upgrade, also known as FTU. Located near Rome and operated by ENEA, FTU is one of the few facilities in Europe that has achieved high-performance plasma operations. FTU has been used to study plasma stability, heating methods, and advanced diagnostic systems. These experiments provide essential data that feed into the design and operation strategies for ITER. Results from FTU have been shared in journals such as Nuclear Fusion and Plasma Physics and Controlled Fusion, making Italy's role academically visible across the global research community. Beyond FTU, Italy is also developing newer facilities. The Divertor Tokamak Test facility, or DTT, is being built at ENEA's Frascati laboratories. The DTT is designed to study one of the most difficult engineering problems in fusion reactors, which is heat removal. A fusion plasma can reach temperatures of hundreds of millions of degrees, but the exhaust heat that flows into the divertor region must be managed without destroying reactor materials. The DTT will allow scientists to test new materials and geometries for this purpose. This project has received strong support from the Italian government and the European Commission. Private companies in Italy also play an important role in fusion development. ASG Superconductors, headquartered in Genoa, has decades of experience producing superconducting magnets for particle accelerators and medical imaging. Their expertise is now directed toward fusion magnets that can withstand high currents and strong magnetic forces. Another example is the company Walter Tosto, which manufactures large steel components for fusion devices, including vacuum vessels. These industrial players illustrate how fusion research in Italy is not only academic, but also involves engineering firms capable of producing the heavy hardware that makes reactors possible. Italy is also part of the Eurofusion Consortium, which coordinates European fusion research under the Horizon Europe framework. Eurofusion funds experiments across member countries and runs the Joint European Torus, or JET, in the United Kingdom. Italian scientists contribute to JET campaigns, particularly in testing tritium and deuterium fuel mixtures. In the year 2021, JET set a record by producing 59 megajoules of sustained fusion energy during a 5-second run. This achievement, reported in Nature, showed progress toward future reactors. Italy's involvement ensures that its researchers are directly connected with these historic milestones. The physics behind plasma confinement is quite complex. Magnetic fields must be arranged in a way that keeps charged particles spiraling inside the reactor without colliding with the walls. Tokamaks achieve this by combining toroidal and poloidal magnetic fields to twist the plasma into a stable path. However, instabilities known as edge-localized modes can release bursts of energy that damage materials. Researchers at ENEA have worked on controlling these instabilities with magnetic perturbations and advanced fueling methods. Understanding these mechanisms requires sophisticated diagnostics, such as Thomson scattering and neutron detectors, which Italy also develops and deploys. Another line of research that Italy supports is inertial confinement fusion. While the primary focus remains magnetic confinement, Italian universities collaborate with international labs such as the National Ignition Facility in the United States and the Laser Megajoule in France. In inertial confinement, powerful lasers compress a small pellet of deuterium and tritium to extreme densities, initiating fusion. Italian researchers have contributed to laser diagnostics and plasma modeling in this area. While still far from commercial viability, inertial confinement provides an alternative pathway that could complement magnetic systems. Fusion research also depends on materials science. The inner walls of a reactor must withstand bombardment by high-energy neutrons released during fusion. These neutrons cause structural damage and activate materials. Italian institutes such as the University of Bologna and the Polytechnic University of Milan study advanced alloys and ceramic composites designed to resist radiation damage. Experiments include testing tungsten and beryllium coatings that can survive repeated plasma exposures. Results are often published in journals such as Fusion Engineering and Design. These studies are crucial for ensuring that reactor components last long enough for practical operation. Heating a plasma to fusion temperatures requires several methods. Italy has contributed to systems such as electron-cyclotron resonance heating, which uses microwaves tuned to resonate with electrons in the plasma, raising the overall temperature. Ion cyclotron heating and neutral beam injection are also employed. ENEA operates test stands for these technologies and has built components that will be used in ITER's heating systems. These mechanisms must be precisely controlled to avoid destabilizing the plasma. Italian expertise in control systems ensures that heating remains efficient and stable during experiments. Comparisons with older energy technologies highlight why fusion is attractive. Traditional coal plants emit gases and pollutants. Fission reactors provide carbon-free power but generate radioactive waste that must be stored for 10,000 years. Fusion, by contrast, produces helium and short-lived radioactive materials. It also has no risk of runaway chain reactions like those that caused the Fukushima accident in 2011. However, unlike fission plants that have operated for decades, no fusion plant has yet delivered electricity to the grid. This gap underscores the importance of ongoing international cooperation. Looking at the near future, Italy's DTT facility is scheduled to achieve first plasma in 2026. This will provide a platform for testing divertor solutions directly relevant to ITER's next phases. Medium-term, by 2029, ITER aims to demonstrate sustained fusion burning with deuterium and tritium. Italy's contributions in magnets, materials and diagnostics will be central to that success. Long-term, the DEMO project planned by the European Union is intended to be the first demonstration power plant producing electricity from fusion, and Italian scientists are already contributing to its design studies. Fusion is not without challenges. One issue is tritium supply, since tritium is scarce and must be bred inside the reactor using lithium blankets. Italy is investigating breeder materials and has proposed test blanket modules for ITER. Another issue is cost. The construction of large fusion devices requires billions of euros and long timelines. Policymakers must balance these investments against other renewable energy technologies, such as wind and solar, which are already deployed at scale. Fusion, therefore, remains a long-term option that must demonstrate competitiveness. Academic contributions from Italy extend to plasma theory and simulation. Universities such as Sapienza University of Rome run computational models that simulate turbulence in magnetically confined plasma. These codes are validated against experimental data from FTU and JET. By understanding turbulence, researchers aim to improve confinement and raise plasma performance. Italian groups also collaborate with international modelling centres, such as the Max Planck Institute for Plasma Physics in Germany. Simulation allows faster exploration of design options, compared to building physical devices for each experiment. The role of journals and peer-reviewed publications is absolutely critical for validating progress. Italian researchers publish in journals including Nuclear Fusion, Fusion Science and Technology, and Physical Review Letters. For example, recent papers have examined divertor heat flux mitigation and novel superconducting cable designs. This constant flow of publications ensures transparency and allows results to be compared across international teams. Conferences such as the European Physical Society Plasma Physics Conference also provide venues where Italian contributions are highlighted alongside other global research efforts. Industrial application remains a key question. If fusion becomes viable, Italian companies stand to gain from manufacturing components and exporting expertise. Companies like Ansaldo Energia could supply turbines for future fusion power plants. Walter Tosto could continue providing large-scale reactor vessels. This industrial base positions Italy to benefit economically from early involvement. At the same time, it ensures that Italian workers gain experience in advanced engineering fields that spill over into aerospace, medical imaging, and other high-technology industries. There are also international competitors in the private sector. In the United Kingdom, Tokamak Energy is building spherical tokamaks with high-temperature superconducting magnets. In the United States, Commonwealth Fusion Systems, spun out of MIT, is constructing compact devices using advanced magnet technology. China is scaling up its East Tokamak with steady-state operation goals. Italy must continue contributing to European collaborations in order to remain relevant in this competitive field. By doing so, it ensures that its research institutions and companies maintain a place at the front of global fusion development. Education and workforce development are also important. Italian universities train physicists, engineers, and technicians who later work at ENEA, ASG Superconductors, and other organizations. Programs supported by the European Commission ensure student mobility across borders so that Italian students can gain experience in other laboratories such as CERN and Culham in the United Kingdom. This builds a network of skilled personnel capable of sustaining long-term fusion programs. Investment in human capital is as essential as investment in physical infrastructure. In conclusion, Italy plays a significant role in fusion research through its national laboratories, universities and companies that contribute hardware and expertise to international projects. By advancing technologies for magnets, materials and plasma control, Italy strengthens Europe's position in the global race toward fusion energy. The years ahead will show whether facilities such as the DTT and ITER can achieve their goals. If successful, these collaborations could set the stage for demonstration power plants in the following decades. Thank you very much for watching. Please like and subscribe.